Okay, so 5.3 is U-Substitution, which is a strategy to integrate, all right? So why would you need or want to do U-Substitution? So basically, here's a little scenario. If you were asked to take the derivative, you can multiply it out, use the power rule, or you could use the chain rule. Now, if I have a higher power though, remember the chain rule is going to be faster. If we had a root, you had to use a chain rule. So the same argument is going to be true for integration. All right. So now if we want to do an integral of products or quotients or different things, we don't have a chain rule per se for integrals. We do have U-Substitution. So this actually does the chain rule, product rule, quotient rule. It's all one. All right. Now, you're going to try to skip some of these steps, and that's where confusion sets in. So your answer might be close, but just try to do all the steps. So in order to do this problem, we could multiply that out 5 times and then distribute the x. But because it's a product rule and the way things are set up, very specifically, that's important, we're going to be able to integrate that using U-Substitution. And it's not even a super long process, but you need to get used to it, okay? So I'm going to do things in a box, and I would suggest that you do it. So we match things up, things like that. Okay. The process, important notes, okay? The process of U-Substitution. Every year I have students try to skip this. They don't write it out. You're not forced to write it out, but it is actually going to be really helpful when problems get more complicated. So if you have good strategies now, honestly, you won't even realize that the problem's harder because it's just going to naturally flow, all right? So it is really important that you define these variables. You won't really understand why until the problems get harder though, all right? So I'm going to call it matching. But whenever you want something to match up, this is super, super, super important. You can divide by a number, but you are never going to be allowed to divide by a variable. It does not create the correct answer. It might seem right, but it's not. The very last step, because these are all indefinite integrals, is always just going to be to add c. So we kind of ignore it until the very end. But anything that is not just a simple power of x, like with the power rule, we have to use U-Substitution, okay? So for trig, anytime you had something that wasn't just, and I'll say and trig, that wasn't just sine of 4x. If it's more than just x, you have to do a U-Substitution for trig, all right? So the problems do get tricky, but this is your practice. All right, so let's look at example number 1. I notice I have a quantity. Notice I don't just say a power of x. So I have a quantity to a power of 4. In calculus, there is no way that they want you to do all of that work by hand, okay? So what we're going to do is I call it my U box, and I really do make a box over on the side. And what you want to do is you want to start with thinking of this problem as 2 different functions, because really the chain rule, remember, was composition. So I really want to think of this as something or a quantity to the 4th power. So I think of 3x minus 2 as one thing, and I think of something to the 4th power as my other thing, okay? So it's 2 parts. So we have 3x minus 2, and we also have some thing to the 4th power, okay? That's composition. So what we want to do is we can take care of this with the power rule. But what do we do with that inside quantity? Well, that's typically what your U is going to be. So you're going to define that variable, all right? So U equals 3x minus 2. Don't worry about the power. So the whole idea is you want to think of what 2 things are going on in the problem, okay? The part that's not just easily fixed with a power rule for integrals is typically your u, okay? But it does get harder. So what we want to do is we want to ignore the problem. We want to just look inside our box. So I'm going to take the derivative of u, and we're going to take the derivative of both sides. So the derivative of u we write as du. The derivative of 3x minus 2 with respect to x is 3. The derivative of negative 2 is 0. And then I write dx to show that I took that derivative. Okay, I have a du on the left because we took a derivative, and I have a dx on the right because we took a derivative. Now, what we're going to do is called matching with our u box. We want everything in here to match up on the original problem, and we might need to manipulate some things. So if I see this, so our goal is to get rid of all x's in the original problem, okay? That's the whole idea. And use u's, okay? But we can't just do that. So where I see 3x minus 2, that's u. So I've got this, the integral of u to the 4th. Now, I have dx, okay? I have a dx here, but I actually have a 3 times dx. Well, I just want dx. So what I can do is I can divide both sides of this. There's like a 1 here. I can divide by 3. And so if I see dx, I can write 1/3 du. So here's 1/3 du. And I'll write it down here. Now, everything matched up, okay? There's no x's left. This 1/3 is a constant that's being multiplied, so I'm going to bring that out in front. And this all gets to stay. Everything's being multiplied, so remember the order doesn't matter. Now, this means it's u to the 4th with respect to u as the derivative. So we can just do a power rule. So I'm going to keep the 1/3. I'm going to add 1. And then it's plus c. So actually get u to the 5th divided by 15, or 1/15. It's really up to you how you want to write this, plus c. Now, that's great. We've integrated, but we just temporarily changed everything to u so we could do this chain derivative integral kind of thing about. So what we want to do is we want to go back to our u box, and we want to plug this u back in. So I get this u, which is 3x minus 2 to the 5th power divided by 15 plus c. And this is the original function. Okay? Now, it might seem like, well, wait, couldn't we have just done all of that in the beginning? Except you would have done, 3x minus 2 to the 5th divided by 5, but notice how it's 15. Because remember, when you take the derivative, you have to account for the derivative of the inside. This really is doing that accountability for you, okay? So it's U-substitution, and it kind of is the chain rule for integrals, all right? Let's look at example number 2. So we have a 4 being multiplied by something to the 2/3 power. So really I have something inside and I have a power. This 4, remember, we really could think of outside, so it's not super important, the 4 is. So I have a power. You typically don't use your power in your U box because we can do the power rule to take care of that. So what we want is we want U to equal whatever's inside. And that's typically your strategy. It's the inside function. Now, don't worry about matching things up. Ignore the problem and actually just go to your box and do the math, ignoring everything else. Don't try to make things match up while you're doing it. So the derivative of u is 1 du. The derivative of 6x minus 1 is 6, and it's with respect to x. Now, we're going to try to match things up. So this is u. I have a 4, which I can put on the outside. And then dx, remember I can divide by 6. So 1/6 du equals just dx, because I divided by 6. So if I see dx, which I do, I can write this. Now, this and the 4, because everything's being multiplied, can come out. So we have 4/6 integral u to the 2/3 and the du. Notice, everything's matched up. I'm not just crossing things out. I don't have this. I don't have that. I'll even make them darker. So I just wrote everything nicer. Now, since everything's in terms of u, we can integrate because that's just a simple u to a power. So that's a power rule. That's why we do this. We can't integrate with a quantity. You can only integrate simple powers. That's the purpose. So I get 2/3. I'm going to add 1. Remember, that adds the powers together. And then I multiply by the reciprocal plus c. So let's see, those reduce. So I get 2/5. I'm going to plug the u back in to the 5/3 plus c. Okay, so you'll notice the problem is similar, but the numbers are always just slightly different because of that derivative that we had to account for. So I really don't skip this part. Don't skip. It's actually super important because of this whole part down here. The dx is probably the most complicated part. I don't know how people do that in their head. All right, let's try something that looks a little different. We have an x on the outside. We have an x squared minus 2, and we have a power. So I'm going to rewrite this first as x, and then we always want to rewrite this as powers anyway. Okay. So this time we have a variable. We can't pull that out because it's not a number. So I have x minus 2, and I have a power. Well, the power I can do with a power rule, so I'm going to ignore that. So I have to pick, do I want x squared minus 2 to be my u, or do I want x? Because they're separate. So in general, you want to pick the higher power because we're going to be taking the derivative. Okay, so I'm going to make a little box. So I'm going to pick the whole thing, x minus 2. So the derivative of u is du. The derivative of x squared minus 2 is 2x dx. Now, what happens is let's cross this out. So let's substitute, sorry, not cross out. So x squared minus 2, that's u. I can leave the 1/2. And then I have this x dx. Well, we kind of have that here. So if I see this, well, I don't see a 2. So we can divide by numbers though. So 1/2 du equals x times dx. So if I see this, which we do, I can substitute 1/2 du. So I always put the 1/2 in front, and the du is going to go at the end. Remember, all of these are being multiplied, so the order does not matter. So we really have 1/2 u to the 1/2 du. The 1/2s are just coincidence. And we can integrate with the power rule. So 1/2, add 1, multiply by the reciprocal, plus c. 2's cross out, so 1/3. Plug our u back in. And that's why if you have this box here, it's really easy to find what your variables are. And so now, if we have two functions being multiplied, we can hopefully take care of it with our little u box. And that's what I refer to it. It is your U box. So in general, you want to pick something inside as your U, the higher power as your U, things like that. Okay? All right, the next problem. We're going to rewrite as, I've got x, and then I've got 2x squared minus 1, and this is to the 1/3, so negative 1/3 power. Okay, well, I have a product here, and it looks pretty complicated, so that's also my hint. Yeah, I probably need to do a U substitution. It's not just a single power of x. So once again, I've got x, 2x squared minus 1, and a power. Well, I usually pick the highest quantity to be my U. And if it doesn't work, we'll be able to tell. So take the derivative. Don't skip this part. This might seem silly, but this is important before you look at what you have. So bring down the power. I get 4x. The derivative is 0, and so dx. So then I start looking what I have. So I think, okay, well, this is U. I have an x dx, which I see right here, so I don't want the 4. So we can divide by 4. So now if I see x dx, I can write 1/4 du. So we get 1/4 u to the negative 1/3 du. And see, everything matched up. I didn't force it, and I just have a single power of x that we can integrate with the power rule. 1/4, add 1, so I get 2/3, multiplied by the reciprocal, plus c. Well, nothing cancels, so I get 3/8. U is that to the 2/3 plus c. Okay. All right. Now, I know I make it look easy picking U. That is the hardest part. So I can definitely work with you, and I'll ask you what to pick. But let's try a few more. And notice I have 10 examples. So there's a lot. So if you want to fast forward, you can. But you'll definitely want to hit number 10. Okay. Notice I have some trig here too. So let's try number 5. Now this one, because they're being subtracted, I can do them separately. So I've got the integral of x minus the integral of 3x to the 1/2. Well, the first part, that's just a power rule. So I get x squared over 2. I don't write a plus c because there's just 1 plus c at the end. Now, this one looks like I should do a power rule too, but because I have 3x, you technically need to do a u substitution on just the second part. So the u is going to be the inside. So the derivative of u, the derivative of 3x, and then we'll go to match it up. This is u. I don't have a 3 dx, so we're going to divide by that. So wherever I see dx, I write 1/3 du. And so now everything matched up. So I'm going to bring the 1/3 out. I've got u to the 1/2. Now notice I still have my integral symbol because we haven't integrated the second part. So this stays. And I get 1/3. We're going to add a power. So 3/2 multiplied by the reciprocal. And then 1 constant at the end. Now notice this is in terms of u. So I need to go back and substitute my u back in. So x squared over 2 minus 2/9, 3x to the 3/2 plus c. Okay. So don't overlook, anytime you have a quantity, you do need to do a u substitution. All right, let's try some trig. So once again, it's not just sine of x. So sometimes your u will have a trig word with it. Sometimes it's just the inside of the trig. It really depends on the function. If you just have one trig word, I could integrate sine. So that means that I want this to be my u. So u equals 1 minus 3x. See, this would be like a chain rule for a derivative. So du, that's 0. We get negative 3. And we'll go to match this up. So here's u. Now, I don't have a negative 3 dx, but I do have a 3 and a dx. So I really just want to divide by negative 1. See? So when I see 3 dx, I can just write negative 1 du. So if I write this, I get negative 1 sine of u du. Okay, so I don't have to divide by the 3. If I have a 3 here already, you should just leave it. Okay, so now I need to think, what function has the derivative of sine? Well, that's negative cosine. Okay, so then 2 negatives make a positive. I get cosine of u. I want to plug back in. And then you can check yourself. Oh, is the derivative of cosine 1 minus 3x using a chain rule positive 3 sine, blah, blah, blah. Okay. All right, this one. Once again, I have a trig function, but only one. So I'm going to let u be the inside. 4x is not just x. So anytime it's not just x, even if it's not being added or subtracted, you do need to do this U-substitution. So 4, and I don't have a 4 on the outside, so this was u, so I'm going to divide by that 4. So dx is 1/4 du. So I get 1/4 cosine u du. So then I say, okay, what function has the derivative of cosine? Well, that's just sine. So 1/4 sine of u plus c. So then we could plug in u. All right, 8, 9, and 10. So 8, we've got 2 trig words. Sine cubed times cosine. So remember, we can't just do a power rule. So I've got sine, cosine, and a cubed. The power we can take care of with the power rule. So I ignore that. So because sine is being to the third power, I'm going to let u be sine. The other function can be taken care of with our du, possibly. So the derivative of u, the derivative of sine is cosine, and then dx. So this is u, it is cubed, and then I see a cosine x dx, so all of that is du. So see how everything got matched up? So I probably did the right u. And I just have a power rule left. That's how you know you probably did it correctly. So integrate, we get u to the 4th divided by 4 plus c. So then we'll go ahead and plug in sine. So sine to the 4th. Remember with trig, you typically write the power in between. All right, so on number 9, so these we had like one derivative was the other function. So I got to start thinking, like, what's the derivative of tangent? Oh, it's secant squared. I don't have that. What's the derivative of secant? Secant tangent, but I don't have secant tangent and another secant. So I want to go back and I want to look at my trig derivatives. So we know that the derivative of secant is secant tangent. So because I actually have both of these as one function original, I just want my u to be the inside because it's not just x. So sometimes you'll have u as a function, sometimes you won't, but you have to go back to what are those derivative relationships. So du equals 10, and I don't want a 10 in front. So now we're going to match it up. So this is u, and dx is 1/10 du. So I get 1/10 tangent secant du. So if I see secant tangent, I get to write just secant because that's the original function. And the 1/10 stays being multiplied. Does that make sense? So then we'll plug u back in. Notice I don't do too much on one step until you get comfortable. All right, the last example you definitely want to watch. This is going to be tricky. So I call it a hard, and on the homework I also let you know. The thing that kind of sets us apart is that my two functions on the outside and the inside, they're the same power. One's not lower than the other. So that's different. So first we're going to start by, notice we use a quantity here because those need to stay together, writing these as a power. We don't change that strategy. So I have two different functions. And I think, well, this one's to a power, so I'm probably going to let that be my u. And it might not work, but you want to play around. So the derivative of u, the derivative of x is 1 dx. And so, see, I'm not sure yet, but we're going to try to match things up. So this is u. Dx is just du. And so I have all of this left. So it's like, ooh, well, what do I do with that? We have to get rid of all the x's. Remember, that was the goal. So we kind of got to manipulate. I don't want to see an x, but I know this is true. So if I know, I'm going to make another box down here. If we know that we let u equal x minus 2, then if I solve for x, I can add 2. So u plus 2 equals x. And I can substitute that into my original. So everywhere I see an x, I can write u plus 2. So we get u plus 2 is u plus 4. This is u to the 1/2 du. Now, this is still a product. And we don't have a product rule. We're not going to get a product rule. So we got to start thinking, well, what do we do? Well, what do we do with derivatives? We can just distribute though. So remember, this is like u to the first. So when you distribute, we're going to add powers. So 1 plus 1/2 is 3/2. And then both of these are single powers of x, or u, being added. So we can integrate them separately with the power rule. So I'm going to integrate. We're going to add 1. Let's do red. So u to the 5/2 multiplied by the reciprocal. 4, add 1, u to the 3/2 multiplied by the reciprocal, plus c. Now, this time I just have 2 u's to substitute back in, but that's fine. So we get 2/5 u plus 8/3 u plus 1 constant. Now, this one's going to be a little harder to check. I would have to do the derivatives, get a common denominator, and match it up. So trust yourself. But that's the idea. Okay? All right, so on your practice, I give you 3 normal ones, a few trig ones, and I give you 2 practice of the hard ones. Okay? So 9 problems to try. Good luck.